Okay, so this is thermo and electro. So we're going to do some delta H in here too, and then delta S, delta G. So the thermo part 2 with the thermo part 1, which is unit 6, and then get into some electrochemistry as well. So here we go. All right, so this is like where it is on the formula sheet, as you can see, where it is on the formula sheet. All the thermo-electro stuff right here. I put in basic terminology for heat, temperature, surrounding systems, endo, exo, that kind of stuff. Always exothermic for combustion, basic rules. Axing is taxing, breaking bonds is always endo, forming is warming, exo. But when you have both of them together in a reaction, you have to go for the net overall there. Phase changes, solid to liquid to gas, that's always going to take energy, that's endothermic. And you're breaking not really bonds here, although that's what it says. It says bonds. Did I not replug you? I thought I plugged you back in. Okay, there we go. Not really breaking bonds here for phases. It's more like the IMFs or the forces. Some of them are bonds because they're intra forces. Some of them are just IMFs because they're between. They're the weaker ones. And then gas, liquid to solid, cooling curves, whatever. Those are always exothermic. Temperature changes, feels hot to us. Remember, if it's going to the surroundings and feels warm, because the thermometer is in the surroundings, that's always going to be exothermic if the temperature goes down for a forming of solution, or if it's forming, or if it's reacting or forming a solution, feels cold to us, the thermometer, the temperature is going down. The thermometer is once again in the surroundings, so therefore it's endothermic. Okay, so that's an important one to remember. Q equals MCAT, that's on your formula sheet. Once again, if Q is positive, that means the change in temperature increases. That means delta H is going to be negative. We'll probably do one or two like that. So intro to enthalpy. Enthalpy is the amount of heat or absorbed release in a chemical reaction in the kilojoules per mole of reaction. The ways to calculate the Q divided by moles, and that's using the calorimetry data is number 1. Enthalpies of formation, those are provided to you in a table. And then Hess's law is another way. There's also the bond enthalpies. You can get pretty much a good idea of what delta H is going to be there. And writing formation reactions, remember, formation is from the elements to make 1 mole of the substance, okay? Or if you're doing like the combustion of 1 mole, you want to make sure that we're talking about 1 mole, everything gets balanced that way, and so then you might get some fractional coefficients when you balance. Okay, so there's that. And then enthalpies of formations are basically products minus reactants times the moles in the balance reaction. Hess's law. If you flip the reaction, you change the sign. If you multiply, you also multiply the delta H by that factor. And then at the end, you just add up all the delta H's when you merge the reactions to the overall. Method 3, the Q from calorimetry data. Basically, depending on what you're using there to get your Q, the sign usually changes to go from QAQ or to Q reaction or to Q solution. And then you divide by the moles of the reactant or the moles of the solute that's being dissolved. And then, of course, there's bond enthalpy. So this is kind of a reminder of bond enthalpy. That's a bonds broken minus bonds formed. This one's not on the formula sheet. You definitely need to have this one down and memorized. As you can see in the example here, you are able to cancel these ones out because they're the same on both sides of the reaction. So you only really have to use the ones that are not equal on both sides. So bonds broken minus bonds formed. In this case, it ended up being a negative 138. So this ends up being exothermic for the delta H. So entropy, randomness, Microstates, higher entropy, increase in entropy. That is the products minus the reactants, that one's. And of course, universe, nature, increasing entropy is pretty much favored towards disorder, chaos. It increases if moles of gas to products to if the moles of gas products are greater than the moles of the gas reactants. If the gas increases when the volume increases, volume spread, if the volume increases, you have more ability to create more microstates because there's more positions. Entropy increases when a solid turns into a liquid or into a gas. So as you're going from solid to liquid gas, your entropy is increasing. Dissolving substances also increases microstates. Temperature increases the particles moving faster, more microstates. Check the moles of gas on both sides. Kinetic molecular theory. Distribution of kinetic energy among gas particles broadens as temperature increases. And that's why the Maxwell-Boltzmann distribution bell curves, they have a tendency to flatten as you increase the temperature, because you do have some still moving slow, but you have a lot, some moving super fast, but then your overall average in the bell area shifts over and it flattens out a little bit. Gibbs free energy, delta G, okay. Negative delta G means thermodynamically favored, spontaneous, doesn't need outside energy to occur, okay. There's two ways to calculate it here, products minus reactants, and then the delta H minus T delta S, which we'll be using, yes, a lot of so far. Okay. So this is a good table to do, or if you can just do it based off of the equation, which is kind of how I do it. I just use, and I think about the signs when I'm using this equation. Delta H minus T delta S. Sorry. So you can do it just off of the equations, but rather than just memorizing this particular deal here. I don't know if that's necessary to do so. Anyhow, just saying, yeah, that it might be easier just to do it off of the equation. But endothermic entropy decreases is not favorable at any temperatures. Exothermic entropy increases, always favorable. And then plus is favored at high temperatures. That's driven by entropy. And negative favored at low temperatures, driven by enthalpy, the delta H there. All right, free energy and kinetics. Some reactions are thermodynamically favored but do not appear to make products at a measurable rate. They are under kinetic control. Don't forget, there's always one of these type of questions on there. And that's the kinetic control is usually due to a high activation energy, so it can't initially get started. Catalyst can help speed up the reaction but does not affect the delta G. And delta G is negative, K is greater than 1. Also, E cell is going to be positive. If delta G is positive, K is less than 1, E cell would be negative. Delta G is 0, E cell is 0, K equals 1, all that good stuff. All right, so finally some lovely problems to do. So student wants to determine the enthalpy of solution for potassium nitrite. Luckily, they gave us that. The student takes a sample, fully dissolves it in the styrofoam cup. Density here, that tells me I need to basically change something over from that. That's a key thing. And here is my specific heat. So that's C right here. That variable's right here. Now the thing that you need to remember for this one, this is a Q equals MCAT. This is also dissolution. As you can see up here, we're dissolving. So this is really going to be a Q problem. And you need the entire mass of the solution here. So with the density, this is going to become 91.5 grams using the density there. Plus we need to add it to the 8.5 grams. These two together are going to give us the entire mass of the solution. So our entire mass of solution is 100 grams. Actually, that's 2 zeros there. So we know that now. So 100. This is 4.2. It usually does take on the joules per grams degree Celsius. takes on the specific heat of water because the majority of the solution is water. The final temperature is 19.5. It's always T final minus T initial, like so. So we're going to subtract this, and it's going to end up being negative. I can already see here because 19 minus 22. So we calculate QAQ. So I'm getting QAQ is negative 1260 joules. Okay, and we usually, to do Q solution, we change the sign. So this, because this is from the surroundings perspective, the surroundings getting colder, that means the system's getting warmer. So the system's gaining energy, so this is a positive. And I'm going to go ahead and change it to kilojoules, because delta H is normally, I guess I don't need the zero here, normally reported in kilojoules. Now, approximate enthalpy, this is Q over moles. Okay, so our Q solution, this is going to be moles of the solute too, by the way, if it was moles of the reactant if you were doing Q reaction. So we have 1.26 divided by, and we're going to use this in order to find our moles. So we have 8.50 grams. They told us it's 85.1, and this is back in the day when these were multiple choice questions you were supposed to not do without the calculator. So basically 8.5 divided by 85 gives us 0.1 for the moles. So basically this divided by 0.1 should have made it 12.6 kilojoules per mole. And it's positive because we know that it's endothermic because the temperature decreased. So the answer then is D, like so. Which of the following statements is correct regarding the favorability of this process? Well, we know it's endothermic because delta H is positive here. Positive delta H. We also know that the entropy increases because we're dissolving. So this is going to be a plus-plus situation. And this should be entropy driven. Favored driven by enthalpy and entropy? No, it's going to be favored only by the entropy because the enthalpy is endothermic. For the reaction to be endothermic, the magnitude of attractive forces between the dissociated ions and the dipole of the waters. So these are the ion dipole forces formed. The forming is warming part. They must be smaller than which of the following? And technically, you know, there's two things. You have to break the ionic bonds first between the K and the NO2. That's what there's talking about, the strength of the lattice here. Those are those ionic bonds that has to break. You also do have to disrupt the intermolecular forces between the water molecules, but this doesn't, I think, take as much energy as breaking the ionic bonds. So they're saying the answer to this one is D. B is saying the same thing as the forming of the ion dipole forces. This is the ion dipole forces that are formed. It's starting to delay again. This is getting annoying. The ion dipole forces, that's the formed forces. You have to break the bonds between the ionic solid, and you have to disrupt the hydrogen bonding in the water, but the more important one that has to be higher because the first part, breaking bonds, has to be higher than the forming in order for it to be endothermic. After data is gathered, the student notices that not all of the sample has been dissolved. So not all of it actually dissolved. How would that affect the calculated enthalpy of solution? So basically what's going to happen here is if it doesn't all dissolve, we're really affecting this particular measurement right here. because in order to separate the K from the NO2, it has to draw energy in from the surroundings. So the temperature should really have gone down further. So that's going to make QAQ, this number right here, smaller than it should be, which then translates to a smaller Q solution. So when we divide the smaller Q solution by its moles, then this delta H ends up being artificially low. Look at the calculated answer is lower than it should be. If all of it had dissolved, the final temperature would have maybe dropped to like 18 or 16, something lower. You would have gotten a higher QAQ number that turned into a more positive Q solution number. When divided by the moles, it would have been a larger value for delta H. Any questions so far? Good to go? Alrighty. Okay, so 2016 here, the student investigates the enthalpy of solution. 2 alkali metals, lithium chloride, sodium chloride. In addition to this, to the salts, the student has access to a calorimeter, a balanced precision of 0.1, and a thermometer with 0.1. To measure Q or delta H solution for lithium chloride, they add 100 grams of water initially, and then adds 10 grams of the lithium chloride. So that's going to be a total mass of 110 for our solution. After the lithium chloride dissolves completely, the maximum temperature reached is this. So this is going to be T final. Here's T initial, like so. Calculate the magnitude of the heat absorbed by the solution during this process, assuming the specific heat is this. Okay, include units. So yeah, basically doing the same thing we did in the last question. Q equals MCAT, so 110 grams. And then this is using 4.18 this time. And this is an FRQ one, so yeah, you would want to show all your work. So final temperature 35.6 minus the 15 degrees Celsius. This is going to give us QAQ again, like so. So QAQ, this is becoming 9471. I'm going to go with 3 here. So I'm just going to make it 9470 joules. And to switch that to Q solution, I'm going to make that negative 9.47. And this is going to be kilojoules. Just changing it over to kilojoules, move it 3 to the left. Yeah, just go like 1, 2, 3, divide by 1,000. So then we need to find, so this is a heat absorbed by the solution. So that would be this right here.
Is the heat absorbed, is that the QAQ or the Q solution? The Q solution?
Being absorbed by the solution is the QAQ. So that's this one right here, yeah. Because the system is actually releasing energy, so the solution is absorbing it. That's why the temperature is going up. System loses, surroundings gaining, and the solution is considered surroundings. That's where your thermometer is. A little confusing on the verbiage, yes, but now we want delta H. So this is going to be based off of Q solution over the moles of the solute. So this is when we need to change the sign. So this you don't need to do until part 2. This is going to be for part 2. So I already did it, but no, we need it for part 2. So we have our kilojoules. And now I need to do my lithium chloride. So I have 10 grams lithium chloride. And lithium is like 6.94, I think. And then chlorine's 35.45. Let me get that. So this is, sorry, that was my tablet that went out. Are you here, tablet? Come on. All right, you're just going to be a pain, aren't you? Let me fix you. Come on. I don't know why I keep losing it. It's here. Let me try something else. Where'd you go, tablet? I can't find you. Sorry about this. Technology is always fun. It like keeps flashing on for a second and then going away. It's old though, so I'm not. Oh my gosh, what the heck, tablet? Okay, where'd you go? Hold on a second. Let me try one thing. I can't even find my cursor, so. There you are. Pen. Come on. Okie dokie. Technical difficulties. Hold on one second. It's not even like moving it over to my PowerPoint here. So let me try something. Let's try that. Okay, maybe that'll work. Maybe it'll unfreeze it now. So when I try to go over to my other screen, it's not showing my cursor. Let me try to get rid of that. No, it's very unhappy with me. Okay, well, that doesn't seem to want to work. Ah, see, you can see my cursor again. There it is. Oh, and now it's going to crash on me. Look at that. All right, hold on one second. Told you, technical difficulties. Well, anyways, so the was negative 9.47, and we need to find the molar mass of the lithium chloride, which I got. So 10 divided by the 42.39. Got the moles for that. 0.236. 0.236 for that. PowerPoint is continuing to crash here. Why can we not? Here, let me try my task manager. Maybe I can get rid of it faster. It's taking forever to crash. End task. Thank you. Okay. Pulling it back up now. Sorry about that. All right, finally back in business. So we were on this one right here, I believe. No, not that one. This one. Okay. So here we go. For this one, we had bottom one here, delta H solution, and be 9.47 kilojoules. This was negative over, and I'm getting 0.236 moles of the lithium chloride, because you take the 10 grams, and this was 42.39 grams equals 1 mole. And that's where I got that from. So we figure this out. The delta H is negative 40.1 kilojoules per mole. And there we go. There we have it. All right, so this one is an old FRQ. It's based off of like the heating curve. Gives you the 1 mole of aluminum at 298. So calculate the amount of heat needed to purify 1 mole. By melting it, the melting point is 933 K. The molar heat capacity, here you go, is joules per mole K. The heat of fusion right here. So basically, this is more of like a Q equals NCAT plus the Q equals the moles times the heat of fusion for melting. So you have to do those together. So 1 mole, and your C, this is the specific heat in moles, so this would be 24 joules per mole K. And to get up to the melting point, it would be 933 is your melting point, minus the 298 K. So this is how much heat you have to add in order to get up to the melting point. And so this is 1524, but this is in joules, and this one's in kilojoules, so we have to convert one at the end. So I'm going to do the melting part over here. So we have our 1 mole times our heat of fusion, which is kilojoules per mole. So it's basically going to be 10 kilojoules. And then we change this one to 3, so that's 15. So 15, I'm going to go with 0.2 kilojoules from that, plus the 10.7. And this is good to get the aluminum completely melted. So that takes 25.9 kilojoules for the 1 mole of the aluminum, as you can see there. So the next part of the question talks about recycling. So it's kind of like trying to make the question a little bit more, I guess, topical. So equation overall process from extracting aluminum is shown below, which requires less energy recycling or extracting it from the AL. So here's your recycling up here, right? And then here, so if we had recycling or existing or so extracting it from here, this would be justify your answer with a calculation. So 1 mole of aluminum there's 2 moles of aluminum per mole reaction, and then 1 mole reaction is going to cost 1675 kilojoules like so. So 1675 basically divided by 2. So this is going to be like 8, 38 kilojoules. So obviously that's per mole of aluminum. So the one that obviously is going to take less energy is the recycling process, is what we're going with there for that one. That's a classic one. Okay. So this is the bond energy one, broken minus formed. So, you know, you could easily knock out 4 of the C to H bonds because those are over here. So you don't really have to calculate those in. These 2 can go, and those 2 can go. So bonds broken. We have 1 of the C to H's, so that's 413. So that's that one. C to C, 348. C to N, 293. I think I've taken care of that side. Okay, and then minus C to double bond C, 614. That's that one. Plus the one N to H, 391 here. This is going to give us delta H based off of bond energies. So I'm getting, for this one, I'm getting 1054. And this one I'm getting 5, so we subtract. So delta H equals positive 49 kilojoules per mole reaction. And that one ends up being endothermic. So predict whether the temperature of the contents in the insulated container will increase, decrease, or remain the same. So the contents, I guess this is based off of a experiment where they were doing some kind of calorimetry with like a styrofoam container or whatever. So the temperature of the contents of the insulated container should have decreased, because if you're measuring it with the thermometer, it should be from the surroundings perspective. This is endothermic. That means energy is being absorbed from the surroundings into the system. So the surroundings get colder where the thermometer is. And that's what you would say there. But you can check out the perfect wording on the scoring guidelines too. All right, so enthalpy change for the following would be equal to the enthalpy of formation for ethanol. The formation of ethanol. Enthalpy of formation means it has to be 1 of ethanol from its elements. So it's got to be either B or D. But looking at this, you need to have hydrogen diatomic and oxygen diatomic. I'm just going to say it's D based off of those deals. This one is going to 2 ethanol, so that can't be formation. 1 oxygen, 1/2, 3. Looks like 6. That one looks balanced. That looks like the best answer there. Our enthalpy values for simple reactions as follows. Which reaction does the amount of energy released by the formation of bonds in the products exceed the amount of energy necessary to break the bonds? So formation is higher than breaking. That means delta H needs to be negative. The bonds in the product exceed the amount of energy necessary to break the bonds. But, by the greatest amount. Okay, I was like, I'm missing something. It has to be 4. Greatest amount means highest negative number, means that's how much energy is released. You're subtracting the bigger number. So this is bonds broken minus bonds formed. All right, looking here at 26, which of these reactions is the value for delta S the most positive? 1 mole of gas, 1 mole of gas, solid. I'm going to call that one a no. 1 mole, 3 moles. So this is like 2 to 4 moles of gas. 2 moles to 2 moles. This is going to be 3 moles to 1 mole of gas and 1 mole of liquid. So I guess I'm going to go with 2 on that one. That's the biggest entropy jump. So basically, yeah, 1 and 4 are out because they're making liquids and solids. And okay, so that's reaction. We're going to go with 2 on that one. Regarding reaction 1, how would the addition of a catalyst affect the enthalpy and entropy changes for this reaction? I believe it's really no change on that because activation energy was lowered by the addition of a catalyst, which just makes it go faster. I don't think it really changes the bond breaking, bond forming, or the randomness of the equation. So I'm going to go with D on that one. Regarding reaction 5, how much heat is absorbed or released when 2 moles reacts with 2 moles of oxygen? So 2 moles of this one with 2 moles of that one. I believe since we're consuming 2 moles of oxygen to 1 mole of the methane, this one's going to end up being limiting. So like 2 moles O2. In the reaction, there's 2 moles O2 to 1 mole reaction. 1 mole reaction is going to be the negative 890. So this is going to be released also. Heat's being released here because this is exothermic. So we're going for released. It's got to be it's got to be either C or A. And I'm going to go with A, because 2 moles of the methane is going to give me this number, but the oxygen is going to be limiting on it because it's going to run out first. So it's going to be A, because that's actually a limiting reactant problem with delta H in it. And technically should work both of them, but I can see it's 1 to 2, so oxygen is going to run out. So that's the limiting. So piece of unknown metals is heated to a high temperature, dropped in the cup. This is thermoequilibrium, by the way. Given the data and assuming no heat is lost to the environment, approximate specific heat of the metal. So this is like QE. This is MCAT. And it looks like the metal's initial temperature is 98, the water's initial temperature is 26. Together is 28. So this is going to be the metal side. And this would be the water side. The metal's losing, so it gets the negative. The water's gaining. It's really just a plug and chug. So we would do negative for the 10 here. On the metal side, we're looking for the specific heat of the metal. The final temperature is 28 minus the 98 is what started for the metal. The water over here is 100 grams. Specific heat 4.2. And then the initial final temperature is 28 minus 26, so that's like 2. So that's just algebra, figuring out here. So I'm getting 1.20. I'm getting D on that one. So that's an MCAT one. Thermoequilibrium. how much heat is released or absorbed when 2.8 gram of CO reacts with excess. This is just like the one I just did with the oxygen. 2.8 grams, change it to moles. Do the mole ratio in the reaction, and then use the delta H. I'm going to skip this one, but it's basically what we did with the oxygen one, except for you start with grams, change it to moles first, and then you can do the rest of that stoich problem. All right, so this is FRQ here. I do want to do this one, even though it's not, I would say, mostly part of, what would I say, part of a lot of the heat stuff, but it is a collecting over a gas over water one, so I figure we should probably do this because this might appear on the AP exam. It has a little bit of aspects of some thermo stuff in here, but we have ethene, molar mass may be prepared by the dehydration of ethanol. Here's its molar mass using a solid catalyst. You can see the setup here. They gave us delta H, delta S. So 0.2 gram sample, and it is set up above the student, heats it gently, evaporated, and the gas is generated. When the reaction is stopped, the volume is collected. Here's the liters. Here is the pressure, and here is the temperature. But they also tell us the vapor pressure of the water is 35.7 torr. Calculate the number of moles. So A, the first thing you need to do here is remember that P total is going to be like P of our gas, which is the C2H4, what's being collected there, plus the pressure of the water vapor, because that's both in here. Well, unfortunately, they gave this to us in ATM, so I have to do a quick conversion. So I'm going to do, the 35.7 torr, and they don't give this one on your formula sheet anymore, so I don't think they're going to give you torr, but 760 torr equals 1 ATM, so I'm just going to do that quick and transfer that into ATM. So this is 0.822 is the total. That's the atmospheric pressure. So we're going to get our P of our ethene, and this is 0.046. Well, technically, I guess 70 is what it's going to be. 70. So 0.822 minus 0.0470. This gives me the pressure of this to being, oops, I don't know what I just did. Go back. So the pressure then of this is 0.775 ATM. I need that to do my PV equals nRT now. So 0.775. When you're doing gas over water, you always have to find the vapor pressure of the water and subtract it out first. It does tell me the volume, what is 0.0854 liters. That was what was collected in the upside down thing right here. And I don't know if it's probably an eudiometer is what they're called. Could be an upside down graduated cylinder, but we're looking for N. 0.08206 is the right number for the R value, which is liters times ATMs over moles times Kelvin. This is on your formula sheet. And then the temperature is 305 K. So we can find the moles here. 0.77 times 0.0854 divided by 0.08206 divided by 305. All right, so I'm getting for the moles, and I'm going to go with 3 significant digits on this one. So 0.00264 moles. These are actually produced. This is the experimental yield. So this is a good lab type question. What would be produced if it went to completion? So it's saying, like, if we started with this and went to completion, that's going to be, so this is a this is 1, 2 is just regular stoich, so you're starting with the 0.2 grams of, this is ethanol. Okay, I'm not going to bother like writing out that. So it tells us what ethanol is 46.1. So if they give those to you in the problem, use them. So this is F, okay. And then 1 mole of ethanol goes to 1 mole of the ethene. And we can figure out if it goes to completion, this is what it should be. Oops, 0.2 divided by 4.1. So what we should have gotten, if everything was perfect, 433 moles. So then you can do the percent yield very easily. This is theoretical. Okay, theoretical yield. So experimental over theoretical times 100 gives you the percent. So we get 0.00264 divided by the theoretical times 100. So the percentage here is about 60, I'm going to say 61%, 61.0%, or that's what I'm rounding it to. Now, because dehydration is not observed to occur at this temperature, the student claims the reaction equilibrium constant is less than 1. So it's not occur at any, at the 298K, which they gave us this data for that. So do the thermodynamic data for the reaction support its claim, justify your answer, including a calculation here. So really this is just a delta G equals delta H minus T delta S. And so I'm just going to plug for C over here. We have delta G equals 45.5, and this is in kilojoules. So don't forget that you need to change this over to. So minus 298 times this one, which we're going to move it over 1, 2, 3 to make this into kilojoules, like so. 0.126. And we calculate this. And I'm getting delta G equals 7.6 kilojoules, where it is a positive value. And so when delta G is positive, K is less than 1. So I support the student's claim that the equilibrium constant is less than 1 because delta G is positive. And that's really all you need to say there for that one. Okay. Alrighty. Now moving on. So this one favored at lower temperatures but not favored at high temperatures. Low temperatures, you need to have negative delta H, so it's got to be either B or C. And you have to have a negative entropy. So this is a negative 1. So I'm going to say B, it's going to be B. So you need exothermic with a decrease in entropy for it to be effective at low temperatures. And we have 1.5 moles of gas on the left there and a mole of gas on the right. So the entropy is decreasing for B, and then delta H is negative. So that's how I would do that one. Here, this is a plus plus. Okay, so solid carbon dioxide, this is a phase change one, commonly known as dry ice. Dry ice is kept as solid by sealing it into high pressure. When the valve is released, the decrease in pressure causes it to sublime. This reaction predict the signs of the H and S. Well, S is increasing. That's positive because it's going from solid to gas. But we know that solid to liquid to gas is endothermic, so it's got to be plus plus. So you need energy to overcome forces holding the particles together. This one right here, the equipment is provided so the student can determine the value of the molar heat solution for urea. Knowing the specific heat there lists the measurements that are required to be made during the experiment. So you need to find the mass. Okay, so we need mass of your solute, which would be the urea. Okay. You're going to need to know the mass of the water because you have to combine those together to get the mass of solution. And we're going to need to take an initial temperature and a final temperature once combined. So list the specific measurements required. So we need to measure the initial temperature, the final temperature, the mass of the solute, the mass of the water, and add those two together to get the mass of solution. And they tell us specific heat here, so that gives you your factors in the MCAT. That's going to give you your QAQ. All right, so showing an equilibrium between the solid and the aqueous here for the dissolution process. Gave us the S, the entropy. Change for dissolution as positive, using the information to calculate the molar entropy for SAQ. So basically, it's just delta S solution is going to be S products minus S reactant. Let me put the S in there too. So then we know this is 70.1 for the solution. We don't know the product, so that's the one we're looking for, minus our solid to begin with. And we can work backwards to find the reactant. I mean the product there. So, and that would make sense. The aqueous is going to be higher in entropy anyways. So just add the 104.6 to the 70.1. So the S for product here is 174.7, and this would be joules per mole K, because we're looking for, yeah, this one right here. I guess you don't need the deltas here. It's just S products minus S reactants. So using the particle level reasoning, explain why delta S solution is positive for the dissolution of urea. That the solid particles that are in fixed position, held together by forces, have now broken apart and are being surrounded by water molecules, creating a lot more microstates. This is kind of what I'd say, but you can check out the scoring guidelines on that one to see the specific wording. But adding microstates, more randomness from going from a solid to being dissolved and being spread out amongst the water molecules, that kind of thing. Student claims that delta S for the process contributes thermodynamic favorability of the dissolution of urea at 25 degrees. Use the thermodynamic information above to support your claim here. Well, it definitely, a positive entropy at let's see here, and since we're dissolving it from a solid to aqueous, that's an increase in entropy. We don't know whether it's endo or exo on here, so but yes, positive entropy times its temperature is going to give a, make delta G more negative, I would say, in the delta G equation. I guess you could cite this one. So this is the factor that's going to make delta G more negative, like it's going to give a higher negative value because the change in entropy is positive times the temperature, that's a negative factor. Hopefully enough to override the enthalpy factor, which we don't know the enthalpy factor because we weren't given any information about it. It might have been in the previous part of the question because this is E through H, but we could, you can always check out the, like I said, the scoring guidelines on that one for specific wording. Let's see here. Oh, it's right here. Thermodynamic favorability is determined by the sign of delta G. Since is positive, that term makes the value smaller, thus making the dissolution more. So basically what I said there. So here's the scoring guidelines. You can see them. There you go. All right. So since we're about halfway. Okay, I'll probably do this one. This one's a more recent one anyways. And then I'm going to start moving on to electro because I want to make sure we're getting enough electrochemistry in here. So high temperatures, silicon tetrahydride decomposes to form solid silicon and hydrogen gas. Write a balanced equation for this. So that's pretty easy. Please don't tell me it's freezing on me again. Please don't do this. Okay, so we have SiH4 decomposing here's into silicon plus H2, and we need 2 of those. So that's we're writing a balanced equation for the decomposition there. Explain why the absolute molar entropy of the solid silicon is less than that of the H2 gas. Well, solids particles are in fixed position, held together by stronger forces. In this particular case, by the interparticle forces of silicon, whereas hydrogen is a gas, which it has more motion, more kinetic energy, things like that. So therefore, the gas is going to have the higher entropy. So go to the phase, solid phase describing the particles. Solids are close together, held together in fixed position, aren't going to have a lot of microstates. They can vibrate in place, whereas the gas is in constant random motion, bouncing off the walls of the container, filling the container completely, really spaced out, therefore has a lot more microstates, something of that, a lot more randomness. So calculate the value here for delta S. All right, so once again, delta S is going to be the products minus reactants. So we have, for the product, we have 18 for the silicon, and we're going to have 2 times the hydrogen. So this is the products, S products, minus S reactants. In this particular case, that's going to be the 205 minus the 205. 18 plus 2 times 131 minus the 205. So I got this equals 75. And remember, the moles cancel out because of multiplying by the moles in the equation, 1 mole or whatever. So the units really should just be joules K, joules over K. It says the reaction is thermodynamically favored at all temperatures. Explain why the reaction occurs. Or sorry, if it is only thermodynamically, no. Sorry, it is saying it is at all temperatures. Explain why the reaction, though, only occurs at high temperatures. This is that phrasing of the weird one where basically they're saying it's under kinetic control. So it's not performing at any measurable extent at the lower temperatures. You would cite kinetic control. and that it has a high activation energy. And so that was basically what that one was hinting at there. So why does it only occur at high temperatures? Because you need the high temperature to overcome the high activation energy. So site kinetic control here, and then high EA, which is I'm abbreviating it for activation energy. So you write out that word for you. So here, this is their scoring guidelines, and they said high temperature is required for the reactant particles to have a sufficient thermal energy to overcome the activation energy of the reaction. Kind of deal. Okay, below's okay. So we're starting to get in some redox now. Okay, so that's going to lead to electro. Below unbalanced reaction occurs when a solution of potassium dichromate is titrated in the solution containing aqueous iron 2 ions. Okay, which species is being oxidized and which is being reduced? Well, I can already tell right now that this is +2, this is +3. So I'm going to say that iron is being oxidized. So it's either B or D for me now. We should, H is not changing, O is not changing. This is +1, -2. This is -2, +1. So it's got to be this chromium here. So that's -14 for the oxygens because 2 times 7. This has got to equal -2. So the 2 chromiums have to add up to 12. So the chromium's got to be +6 here. So chromium's being reduced. So it's got to be D because it's going from +6 to +3. All right, this is a delta S one, but basically, yeah, you're just looking for which the fine would have the most negative. So look for the one that the entropy is decreasing the most. All right, so galvanic cells. Here's some nice review here of those. Okay, so galvanic cells, you can see the anode is going to be where oxidation, anox, red cat. Salt bridge is going to maintain the neutrality of the solution, so the cations of the salt bridge always go to the cathode where it becomes more negative. The anions of the salt bridge always go to the anode where it's going to become more positive because the electrons always run from anode to cathode. Okay? The anode and cathode, or the electrodes, are going to be the solid part of the reaction unless the entire reaction is aqueous and is an ion solution. Then you need an inert electrode, which would be platinum, or like graphite, something of that nature there. And this is spontaneous. Delta G is negative, E cell is positive, K is greater than 1. There you go. So this one compares, galvanic cells, another description of them. I guess I'm not going to sit here and oxidation reduction, salt bridge, all that good stuff. Okay, so calculating E cell. And I know the problem set in the textbook tells you to just stick to the reduction potentials, but I don't like doing that way. I figure out what's being reduced. I figure out what's being oxidized. I flip the reduction potential to change it to an oxidation potential, and then I add them together. And for galvanic cells, it should always be positive. Potential with the delta G equals negative NF E cell, Faraday's constant, the moles of electrons, Faraday's constants on the formula sheet, so you don't have to memorize this. Delta G comes out negative, you know that it's a favorable reaction, okay? Higher E cell positive, that's going to give you a more negative delta G. Here, non-standard versus standard. This is where you need the Q. Q is greater than 1. Q is less than 1 deal. You can use the Nernst equation to explain it, but it's harder and it takes more energy to do so. So what are the main points here? If Q increased above 1, the system is moved closer to equilibrium, cell potential decreases. So basically, that's where you have higher concentration in your products than you do reactants. If Q is decreased below 1, cell potential increases, you have more reactants than you do products, okay? And then, of course, standard conditions is when Q is equal to 1, because that whole part of the Nernst equation cancels out, because it's like ln Q, so that becomes ln of 1, which is going to make it 0. All right, so this is the Nernst equation. There's two different versions of it, but the top one up here, this is the one that's on the formula sheet. Like I said, if Q is 1, this whole part goes away, so non-standard equals standard E cell, okay? But here you're really looking for the Q value and doing the Q comparison. So Q greater than 1, Q less than 1 idea. I like this chart. This is a good one. I found this, I think, on one of Michael Farabaw's notes, because that kind of shows you how to calculate Q with the aqueous. Q is less than 1. Non-standard is greater than standard. Decreased product or increased reactant compared to standard conditions. So this is a good one to look at. Q equals 1. They're the same, E standard and non-standard. Product equals reactant in terms of their concentration with the brackets. Q is greater than 1. Now the non-standard is less than the standard. Increased product, decreased reactant compared to standard conditions. And then, of course, if Q is equal to K, whatever, E cell is 0, you basically have a dead battery. Okay, so that's a good one to study. Electrolytic cells, and this is a good, once again, I think I found the nice chart to the right with the Michael Farabaugh notes, but it kind of puts everything together. The galvanic cell, delta G is negative, electrolytic cell, it's positive. E cell is positive for galvanic, negative for electrolytic. Anode is always oxidation, cathode is always reduction. Direction always goes from anode to cathode. But remember, in the electrolytic cell, it's just basically opposite because it's making the E cell negative. So when you flip the reactions, you're flipping the sign on the E cell. Salt bridge is not required. It can just be all in solution, as you can see in this picture here, because the battery is going to run the electrons through the solution, okay? The salt bridge you need to have or in the galvanic you need a salt bridge because you have to maintain neutrality or you won't get directional flow. The battery makes it do directional flow, so keep that in mind, okay? And then the electroplating stoichiometry we just did, but we'll do a problem or two of this. I'm sure you'll see it, but that was just in the last set of notes. All right, so which of the 5 molecules does a sulfur atom have the lowest oxidation number? Well, this is just another like oxidation one. So this is going to be +4. This one is +2. This is -8 +2. This is +6. Wait, is that right? This is -8 +2. Lowest oxidation number, I guess, is B, because these two are both +6s. All right, so above reaction takes place in a galvanic cell, has a standard reduction potential of positive 1.24 volts. At 25 degrees, standard conditions, which of the following would decrease the voltage for the cell? Doubling the mass of the electrode. Well, the electrode's a reactant. That's going to not really do anything. It's just going to give you more reactant. Adding a catalyst, that should just speed it up. Increasing concentration. If you're increasing reactant concentration, that's going to make the E cell increase, so it'll be non-standard. And then adding water is going to decrease the concentration, I guess, of both. So decreasing the concentration of your reactant would decrease your voltage. It doesn't say which side we're doing it to, so I don't know. This one seems kind of strange to me, but let's check. I'm thinking it's D. Connected to equilibrium, although I don't like the way that's phrased, but I didn't make up that question, so don't blame me, but D seems to be the only one that worked with that particular question, even though I don't like the way it's worded because it's assuming that you know which side you're adding water to, and it doesn't specify. All right, so which of the following would cause an increase in potential in the voltaic cell? Voltaic is the same thing as galvanic, if we haven't mentioned that. described by the above reaction. So increasing this would work. Decreasing that would work. The solids I don't think really play. So increasing Fe, no, that's actually going to make E cell go down. But if we decrease the concentration on this side, whereas this side has more and this side is less, C would work. That would cause Q to, in that particular case, Q would become less than 1 if you decrease the, because Q would be the concentration of the Fe over the Ag squared. So if you made this number, so then now Q goes less than 1, whatever. There you go. So I'm going to go with C on that one. Here we have 2 reduction potentials. A piece of potassium is added to a solution of hydrochloric. The metal starts to react. Which of the following is correct net ionic for the reaction that is occurring? So the only way this works really is if we flip the bottom one. Flipping the bottom one puts K, and we're going to have to multiply this one by 2. So we're going to get 2K going to 2K plus those 2 electrons. That's going to make this positive. And so 2K, 2 H's, 2H plus 2K, 2K plus H2 is D. It's D. Oh, look at this. Lots of fun multiple choice. What would the cell potential be for the galvanic cell constructed from silver to silver plus and Fe to Fe2 plus half cells? Okay. So now we're looking at the silver and the Fe. So if I wanted galvanic, which is what, so I have to flip this one. Okay. So if I flip that, this becomes positive. So 0.8 plus the 0.44, that's going to give me C as my answer. What would the net ionic be? Well, we flip this one. Iron would be over here. We got to multiply this one by 2 for the electron purposes. So this is going to be iron plus 2 Ag plus going to Fe2 plus and 2 Ag solids. And that one is the top one, right? That's this one. A. Okay. A 2 amp current is applied to beakers containing identical volumes of each of the following 1 molar solutions. In which beaker will the greatest mass of metal plate? What? Oh, I don't like this question at all. All right. 2 beakers containing identical volumes of 1 molar solution. Power source. Which beaker will the greatest mass of metal plate? So let's look here. All right, so for the silver one, silver reduction is 0.8. The water reduction would be 0.83. This one wouldn't plate here because it's a positive E cell. So I think doing the source or trying to run it electrolytically doesn't work very well. Copper turning into here, that's 0.34. Iron, though, is negative 0.44, so this one you could plate, and it's less than the water. Aluminum is the most negative. I don't know exactly what they're trying to say will be the greatest one. Let's see what they say as the answer. I honestly haven't seen one. I don't think they're going to give you anything that complicated, but let's just see. 8. Current applied to beakers containing identical volumes of each 1 molar solution. So they're saying it's silver. It's the most positive reduction potential. I guess running the current will make that one go the fastest. Oh, I don't know why they put that kind of question in. I think that's an older question. I don't think they're going to ask you that, but anyways, they're saying it's A. And I'll have to look that one up a little bit more detail, because they don't usually have electrolysis ones be where they have positive potentials, but okay. All right. Current is run through the solution of pure water, and gases are collected and shown above. Which of the following correctly identifies the cathode and anode during hydrolysis, along with identifying the gas present at each? So this is pure water. So pure water, in order to react, is going to have to flip and be oxidation. So the gas that would be produced here is O2. So that would be at the anode. You're going to have, at the anode, you're going to have oxygen. At the cathode, you would have hydrogen. So, and looking here, oxygen is 1 mole for every 2 moles of water, and for the water down here, 2 moles to 1 mole of hydrogen. But if we're running water together, we would need to double this one, because we need 4 electrons. So this actually turns into a 4, and this turns into a 2. So the hydrogen should be outputting at double the rate of the oxygen. So this side should be the hydrogen side. This side should be the oxygen side. This is the anode. And this is the cathode. Because if you're looking at the little bubbles, this one has more bubbles. So the hydrogen output should be double that of the oxygen, because they would have to couple at being or oxidize and reduce at 4 electrons. So this one would double its output. So
but doesn't X have more gas already in the diagram? Isn't that what X is showing?
I see more bubbles in the Y. Do you not see more bubbles in the Y?
Yeah, but there's more space on the X, like above where the
Oh, yeah, okay, I see what you're saying. Since there's more space. You're right. We'll switch those. Thank you. At least my methodology was right. But I didn't even pay attention to the space. You're right. Thank you. So that is true. Gonna go with what you said here. So there's more gas over here. So that must be the hydrogen side. So this is the cathode. And this is the anode. Less gas. So that must be the oxygen. Okay, so X is the cathode and hydrogen. It must be A. Yep. That's a good point. I didn't even look at the space collecting. That one is a very difficult one, though, too. You have to pay attention to everything there. As you can see, it can be easily missed. Which of the following for 10 would not cause a reaction to occur? Adding some aluminum pellets to a solution containing Fe. So adding aluminum to a solution with Fe2 plus. Well, if we flipped this one and added aluminum pellets to that one, this actually turns into positive 1.66 volts. So that one would actually occur. So that one a reaction does occur. So nope, that's not it. Placing a copper strip in a solution containing Ag ion. So copper with Ag. So if we flip this one, this becomes negative 0.34. So we're putting copper in with the Ag here. So that one is also going to occur because 0.8 plus a negative 0.34, that one will occur. Adding powdered ion to a solution containing, so we're adding iron now to the copper one. So if we flip this one, this becomes positive 0.44 added to 0.34. That one also works. Dropping silver coin into a solution containing aluminum. So if we take this one, flip it, this actually, if we take the silver here and flip it to be oxidized, this becomes negative 0.8. And if we put it in the solution with the aluminum that's already at negative 1.66, it's got to be D there. That one would not allow for a reaction to occur because the E cell would be negative between the two. So just flip the solids, make them oxidation, change the sign, and see if it's a positive E cell. That's how you do that one. Okay. Two batteries are connected via the above diagram. The concentration and masses are there. How would the voltage and battery life for the two batteries compare? Oh, fun. So what do we think about the voltages here? Those ones should be what? Everything's doubled for battery Y. So I'm going to go with they're pretty much going to be the same voltage. Because remember, voltage is intensive. The only way to make the voltage change is if you have different amounts, like higher amounts of reactants, less amount of products. That kind of ratio going on. And here they're equal on both sides, just doubled for the second one. However, the one that has more reactants, which would be battery Y, is going to have a longer battery life because it has more to burn. It's going to consume more. It's going to last longer. So I'm going to go and say that this one is D. Yes? Yes. Okay, so FRQs. Here we're going with FRQs. So you have the galvanic cell, 298, 1 molar solution, everything's at standard. Electrode of chromium, electrode of silver. Student measures the voltage of the cell, discovers that it's 0, identify the missing component. Well, hopefully you saw here that we're missing the salt bridge between them. So you would identify the salt bridge and explain that it contains a gel-like substance of dissolved ionic compounds that won't mess with the reaction. They're inert, won't mess with the reaction, but they maintain the neutrality of the solutions to keep the electrons flowing from anode to cathode. The student adds the missing component, measures it to be 1.54. As the cell operates, the silver ions are reduced using the information in the table above. Calculate E cell for this bottom reaction. So I'll do it over here. We have E cell equals E red plus E ox. Now it tells me that as the cell operates, that silver is being reduced, so that's going to be this number. It's being reduced. So this is 1.54. We can find the oxidation potential. And then we just change the sign to get the reduction, because it wants it in the chromium as being in the reduction potential. So this is 0.74 as an oxidation potential. So that means it's a negative 1.74 voltage when it's E red for chromium. It's just the opposite sign there. Right, then balance net ionic. Well, all you have to do is multiply this one by 3. Flip the bottom one. So we get 3 silver ions plus the chromium solid. That's going to 3 of the silver solids plus chromium 3 ion, like so. Balance it by the electrons, yes. So you would show that you're multiplying this one by 3 and then crossing out those electrons. Calculate the delta G for the overall in joules per mole reaction. So we don't have to do kilojoules for that. This is the delta G equals negative NF E cell. So negative 3 for the mole of electrons times Faraday's constant, 96, 485. This is coulombs per mole electrons. And then the E cell voltage, 1.54, and that's joules per coulomb. So you can see how the things are going to cancel. So moles cancel with moles. And then the coulombs cancel with coulombs, and we're going to be left with joules. So this is a super big number. I'm going to base it off of this one, 3 significant digits. So 4, negative, of course, 6, and then 1, 2, 3. That's joules per mole reaction. That one wasn't too bad. All right, so this, and you can go through this, but like salt bridge is missing. Salt bridge allows cations to flow to the cathode, anions flow to the anode to maintain electrical neutrality. So this was, and they have these on AB Classroom as well, where they're going to show you student responses and say this one earned a point, this one didn't earn a point. So like here in the scoring guidelines, salt bridge allows for migration of ions to maintain charge balance in each half cell. So that would be, and then like the top A person, as student A, they got the point, but B and C did not. Salt bridge missing, electrons cannot be transferred. So it doesn't talk about the neutrality of the solutions. And then part C here, the salt bridge necessary to order maintain non-zero voltage. Like what does that mean? So not explaining the correct reason. This one here, we already did all those parts. So we figured out the E red and the balanced reaction, and then they changed it to scientific notation, but I left it as regular notation, but same deal. All right, so 2014 one here. Still a galvanic cell because no batteries attached. Student is given standard here. Has a copper electrode, a tin electrode. As current flows through the cell, the student determines that the copper electrode increases in mass and the tin electrode decreases in mass. Identify the electrode at which oxidation is occurring. Explain your reasoning based off of the student observations. So we want to know oxidation. All right, so oxidation, if it's, so the one, if copper is gaining mass, so this is copper 2 because this is copper 2 here, it's the one turning into the solid gaining mass, so this one's reduction. So that means tin must be undergoing the oxidation reaction. So this has got to be the tin is breaking down into tin 2 plus, and the 2 electrons are being given off. So this one's losing mass. So the solid is degrading. And based off of this is 2 plus here. This would be 2 plus. That tells me the solution's there. So oxidation is tin. Identify the electrode. The tin is where oxidation is occurring because it is decreasing in mass. Therefore, when it changes into the tin 2 ion, gives off the 2 of the electrons, it's going into solution and leaving the mass of the electrode. As the mass of the tin electrode decreases, where does it go? The mass goes into the solution, because remember the mass is pretty much contained within the nucleus of a atom. So the protons and neutrons in that mass is going to go into solution as an ion. That's where it goes. In the expanded view, the center portion of the salt bridge shown in the diagram, well, it's over here to the right because I didn't have any space below. Draw and label the particle view that occurs in the salt bridge as the cell begins to operate, emit solvent, whatever. Okay, so they're telling me I have KNO3, and if I know that this is the anode side and this is the cathode side, then I know anions travel towards the anode. So the NO, the nitrates are going to move this way towards the anode, and then the K pluses, the cations, are going to move this way towards the cathode. Okay. So draw and label the particle view. Yeah. Showing that. So here is the scoring guideline. Since tin is losing mass, tin atoms must be forming 2 plus ions. That processes oxidation. An E cell must be positive based on the E values from the table. I don't remember seeing the table, but I don't see the table here, so whatever. The mass of the tin electrode decreases. Where does it go? It's going into the solution, because once again that's attached to the nucleus. You don't have to go in that total detail. 1 point is earned for the correct representation of both the K plus and NO3 ions. So if you just wrote them in correct ion form, it says including free electron losses this point. All right, and then 1 point is earned for the correct direction. So that one was a 2-point question. So I guess writing as the ions, 1 point, and then the direction is 1 point as well. Oh, here's a lovely electrolysis question. I know you guys are all loving these ones from the quiz and everything. So let's take a look at the electrolysis question. Non-standard E cell is made by replacing the 1 molar solution of copper and tin in the standard with 0.5 solutions of the copper and the tin. The volumes of the solution in the non-standard cell are identical to those in the standard. Is the cell potential of the non-standard greater than, less than, or equal to the cell potential of the standard? Well, it's going to still go and function off the idea of the Q value. And we said that it's going to be the copper 2 plus the tin gave us the copper solid and the tin 2 plus from the way that the mass and stuff went. So that means the tin concentration over the copper concentration, and it was 2 electrons each. So here, does it change if we go for 1 molar solutions for Q, 2.5 solutions? No, because Q still equals 1. So the non-standard E cell should still equal the E cell here. Okay, so number 1, the cell potential should be the same. The problem is with number 2, both the standard and non-standards can be used to power electronic device. With the non-standard cell power the device for the same time, longer time, shorter time. Justify your answer. Well, if we have half the amount of reactant here, okay, 0.5 molar solution, that means it's not going to run as long. So it's going to be a shorter time as compared with the standard E cell because the 0.5 of the copper will run out and be consumed faster. All right, so here's the electrolysis. Student places a new electrode into a fresh solution. Using information, I don't know why they're placing the tin electrode into a fresh solution of that. That doesn't seem right. I think this is supposed to be a copper one. Or, nope, I'm probably going to go with that this is supposed to be that. I don't know. That doesn't seem right. You're not putting the tin electrode into the copper solution, so I don't know why that is. But using information above table, write net ionic for the reaction between, that would be thermodynamically favorable. Justify the reaction is thermodynamically favorable. So here we flip the bottom one here, and this becomes positive. Still the oxidation reaction. And we add it to the 0.34 here, and we get a positive 0.48 E cell. So if E cell is positive 0.48, that means that delta G is negative. So that's why it would be thermodynamically favored. And then it says calculate the delta G for the reaction, include units with your answer. So basically, you know, we would do delta G equals negative NF E cell, and it would be a transfer of 2 electrons between the copper and the tin. I guess this one's not electrolysis at all. Okay. Well, it's not. So we put in the 2, Faraday's constant, and the 0.48, and delta G would end up being negative. And then here in the scoring guidelines, we can take a look at the answer. So once again, for D1, the Q is still going to equal 1. It's the same. So the concentrations are equal in both cases. Q is 1, therefore the non-standard equals standard. Part 2, the non-standard cell would power the device for a shorter time because the supply of the reactant would be exhausted more quickly. And then here we got the 0.48, or as observations earlier, tin is oxidized, copper is reduced and makes E cell positive. And then here they ended up with, you could have expressed it as negative 93,000 joules per mole reaction or negative 93 kilojoules per reaction. But you'll notice in a lot of the electro questions, they have that negative NFE equation as one of the parts. Oh, this one's an electrolysis one, I think, because we have water and we have other stuff. There we go. Got the 2 waters, got the 2 other stuff. Okay. Dissolving of silver nitrate in pure water is represented by the equation above. It's delta G for the dissolving, positive, negative, or 0. Justify your answer. Okay, now I get where they're going with this one. What do we know about nitrates? Nitrates are always soluble. Nitrates always dissolve. They are one of the snap ions. So this process is spontaneous. It does occur. It's going to happen. So it would be negative. And you would state, like, since nitrate is soluble under all conditions, and this dissolution spontaneously occurs, therefore delta G must be negative. Because we definitely
also stated in terms of the entropy change. That's
well, you can't do that unless you know the enthalpy too, and we don't have the enthalpy.
okay.
Because you have to use delta H as well if you're doing delta H minus T delta S. So that's what I paused for a second because that's where my brain went first. And I was like, wait a minute, can't use that. I don't know anything about the enthalpy. So, but I do know nitrate is always soluble, so it's always spontaneous. I know it's a snap ion, so that if it's a spontaneous process, that I know delta G has to be negative. So we'll see what the scoring guideline says. I pretty much have that. Well, actually, we can advance it and take a look. Dissolving is negative because it's known to be soluble in water. Process must be spontaneous. Delta G is negative. Yeah, so that was the way to go for that one. Delta S for the dissolving is going to be positive. We do know that it's going from a solid to aqueous, therefore it's creating more microstates and breaking apart from the solid, so that one would be positive. The solubility of AgNO3 increases with temperature. Oh, now we do know it's endothermic. The sign of delta H for the dissolving process is endothermic. Justify your answer. So it must be positive because if it increases with temperature, heat must be a reactant. So as you increase heat, more dissolving occurs. That would be what you would say there. Is the answer you gave in part A consistent with your parts B and C? Yes, because spontaneous reactions can have a positive or an endothermic enthalpy. With a positive entropy, that just means that it is more favorable at higher that it's spontaneous and favorable at high temperatures. So it is consistent still with B and C. All right, so C1. So your A, yes, it would be consistent with it. But let's talk about those ones right now while we're talking about it. Delta S is positive because the solid reactant is more ordered than the aqueous products, so more microstates, more randomness. The sign of delta H must be positive to increase with increasing temperature. That the temperature by adding heat shifts it towards the product side, although it's not really equilibrium here because this is a completely soluble one. Heat must be absorbed, so heat is a reactant. There you go. Yes, although delta H is positive, delta S is also positive, thus delta G can be negative when the entropy term, the T delta S, is a greater value than the delta H. So this is where it's positive, and the entropy term overrides the enthalpy term at high temperatures. So you could say that, and then delta G could be negative. All right, so now we're looking at the compound of sodium iodide is dissolving in pure water according to this equation. Some of the information of the standard reduction potentials may be useful in answering the questions. Electric current is applied to 1 molar of the sodium iodide solution. Write a balanced half reaction and so forth. Okay, so, oops, sorry, I did not mean to do that. But the first thing I would do, since this is what we're looking for, is sodium. We're looking for iodine. So iodine is a reactant. Water could be a reactant because this is happening in water. And sodium and water. So basically by doing that, I have now identified which can be my two possible oxidations, which are right here. These are the two that can compete for oxidation. And then these two are my possibles for reductions because, once again, the only three things we have in solution is Na+, I-, and water. So those are our only possibilities for reactants. So write the balance of the oxidation half reaction that takes place. So I have to look at these two. When I flip them, this becomes negative 1.23. When I flip this one becomes negative 0.53. So this one is more positive. So this is the one that's occurring. So for the oxidation reaction, D1, I would do 2I- flip it because I'm showing it as oxidation. Goes to I2 plus 2 electrons. Now write out the balanced half reaction for the reduction. Okay, so we're looking here. Out of those, which one's more positive? It's going to be the water. So for the second one here, it's going to be the reduction of water that occurs. So if you wanted to make iodine, that's great, but if you wanted to get sodium metal out of this one, that's not going to happen. And then we get H2. All right. 3. Which reaction takes place at the anode? Oxidation. That's easy. This is just like the one in the notes too. As you can see, they don't necessarily come up with new questions. They just give you different reactions. Anode is always oxidation. Remember, anox. Red cat, anox. And then, once again, with this one, this is similar to the one that was in the notes. If you're looking at part 4 here, all electrolysis reactions have the same sign for delta G. Delta G is always positive for electrolysis because it is attached to a power source that applies electrical current to. So it's not, it requires an outside energy source in order to run. Therefore, it is non-spontaneous, not thermodynamically favored or unfavorable, because, and then delta G would have to be positive. So delta G for all electrolysis reactions is positive because the reactions are non-spontaneous. Energy in the form of electrical current is applied. There you go. That one's very similar to the one that we have in the notes. 215. Okay. Let me look real quick. Try to look and see if there's anything different. Oh, I'd like to do this one. We haven't done any of these yet. So let's do this one. We'll backtrack if we have some more time, but this one's also more recent. So molten MgCl2, molten, melted, like lava hot. Okay. Can be decomposed into its element if sufficient voltage is applied. The products of the reaction are liquid Mg and Cl2 gas. Simplified representation shown above. Reduction half reactions up here. Overall, related to the overall. Draw an arrow on the diagram to show the direction of the flow through the external circuit. Okay. Well, so this is telling me voltage is being applied. That means this one has to flip to Cl minus, going to 2 electrons plus the Cl2. This has to be negative because this E cell needs to be negative. So this must be, so then it must be going this direction. So this is the anode where oxidation occurs. And this is the cathode. All right. Would an applied voltage of 2 volts be sufficient for the reaction to occur? Support your claim as part of the calculation. Well, to make this work, we have our reduction, E red, plus our E ox to get our E cell. So this is negative 2.34 plus the negative 1.2. So this is going to be 2 plus 1.36. So our E cell is negative 3.73 volts. So would 2 be sufficient? This is a no. It must be, you know, the voltage must be greater than the 3.73 in order to overcome the spontaneous, or not the non-favorable E cell. Must be above, so your voltage would need to be above the negative absolute value of the negative E cell there, so it must be above 3.73 volts in order to run overcome its unfavorability. Now, if the current of the cell is kept at 5 amps, how many seconds does it take to produce 2 grams of the magnesium? Okay, so this one is one of those, I'm going to do it up here. It's one of those electrolysis stoichiometry ones. So we're going to do 2 grams of Mg. And I think Mg is 24.31 on the periodic table, and that's 1 mole of Mg. 1 mole of Mg is equal to 2 moles of electrons because of the 2 here. These are both 2s. 1 mole of the electrons is 96,485 coulombs, Faraday's constant. The amps are 5. Oops, putting that in the wrong spot. Hold on. To erase that. 5 goes on the bottom because coulombs goes down below. So coulombs goes down here, seconds goes up here, so this would be the 5 goes down here. And it just wants seconds, so we get to stop there, which is nice. So 2 times 2 times 9645 divided by the 24.31. I do think that's magnesium. I might be wrong, but I'm pretty sure that's magnesium. And then divided by 5. 2 times 2 times 2 divided by 20. Okay, so 3 significant digits. I'm getting 3175.15. So keep the 3, keep the 1. This turns to an 8. That's what I got. That many seconds. Anybody else get anything different? Or did I put the wrong molar mass for magnesium? I don't have the periodic table in front of me, so that's kind of weird. But anyways, that one, they like to ask that voltage question about the running the electrolytic cell. You have to be, above that to overcome the non-spontaneous nature of the negative E cell. So we have 5 more minutes. I'll backtrack. I guess we can look at this one. Student wants to determine the concentration of hydrogen peroxide in solution. Student can use 2 titrants, dichromate or cobalt. The balanced chemical equations for the 2 titrations are shown below. Half reactions in E cell values. These are all written reductions, so in the table, use the information in the table to calculate the following. What would be the E cell for the reaction between the dichromate and the hydrogen peroxide? Okay, so I'm looking at this one and looking at this one. So which one would I flip to make it still, to be able to run in a titration? You would assume this is galvanic, not a battery attached. So we're going to flip the bottom one here. So this one becomes negative. Have to flip that one. So this one would be E cell is going to be E red plus E ox, and this is 1.77 plus negative 1.33. So that's going to be 0.44 volts. The bottom one, cobalt with hydrogen peroxide. So let's switch over here. Here we need to flip this one because that has to be a reactant. So we flip this one, that becomes negative. So this would be 1.77 plus a negative 1.84. Once again, I have to flip this one because I'm reacting the cobalt 2, so that has to be the oxidation reactant, and this is going to come out negative for this one. So they're going to ask thermodynamic data at the bottom there. So this ends up being 0.07 negative volts. So based off of that, which titrate should I use? Well, I should use the dichromate because it's a spontaneous favorable reaction, and since I'm doing it in a titration and not powering it with a battery, and I expect it to run on its own, it needs to be spontaneous in a reaction. Calculate the value for the reaction chosen between the titrant. So, you know, once again, this one is just another one of these. Delta G equals negative NF E cell 1s. Now you just have to be careful between these two because you have 2 and you have 6 here, so you're going to have to multiply this one by 3. So you're working with 6 electrons here for that one to work. And then the Faraday's constant. And your E cell is 0.44. So just pay attention to the moles of electrons because you would have to do that with that one. So I'm getting quite a large number, and this would be 2.5, or negative, a large negative number, excuse me, times 10 to the 5th, and that would be joules, or I can make it dividing by 1,000 would make this what? Negative 250. If I'm keeping 2 sig figs, that would be kilojoules per mole reaction. So either way, that's how those would work. And then there's this one, which looks like it's another electrolysis one. But we are almost here at the time. I believe, if I'm not correct, yeah, I believe here, like they have this, all of the scoring guidelines, so you can pull that one up and maybe look through it. This one was a bit confusing because it's talking about metal air cells, portable energy source, alkaline electrode. But you could look at it just to get another perspective of how things are phrased. Okay. I would definitely recommend for the FRQ tomorrow to look at more FRQs. Another good way to study for FRQ is to pull up the MCQ progress checks and read the explanations, and you get the wording down so that you can do the explanations correctly. Besides just the regular FRQ practice, you can get better with your terminology and how you explain things. And then, of course, if you have time to do the Unit 9 FRQ and MCQ and the Unit 3 FRQ and MCQ progress checks, to at least to take a look at them before. So for A-Day people, yours is tomorrow, and then for B-Day classes, yours will be on Tuesday for FRQ. Just exposure to as many as you can get in and see. The other ones that are pretty good for FRQ would be, and if you haven't already done so, I know a lot of you have already checked out the Michael Faribault summative assessments for each unit. And because the final exam is going to be more heavy on units 8 and 9, you probably should look through the Unit 8 and Unit 9 summative assessments, those two, and see if you don't have time to go through all of them, obviously. But those are going to be a little bit heavier on the final exam. So anyways, are there any last minute questions here before we call it a day? Nope, all good. All right, well,
Thank you, Miss Sen. Thank you.
you're quite Quite welcome,
Thank you so
everybody.
much.